The Dosan On Changho class submarines, including the On Mu, are designed to excel in various roles, from surveillance and intelligence gathering to strategic deterrence. They incorporate the Korean Vertical Launching System, VLS, a groundbreaking feature that enables them to carry up to 10 indigenous Cheonryong land attack cruise missiles and Hyunmoo submarine-launched ballistic missiles, SLBM. These submarines are the first in the South Korean Navy to possess this advanced capability, significantly enhancing their offensive and defensive potential. Compared to their predecessors, the Dosan On Changho class submarines feature numerous technological improvements, underscoring South Korea's commitment to innovation and self-reliance in defense technology. One notable upgrade is the incorporation of Samsung SDI lithium-ion batteries, which enhance the submarine's energy storage and efficiency. This cutting-edge battery technology contributes to improved underwater performance and endurance. The On Mu submarine boasts impressive specifications, making it a formidable force in the South Korean Navy. When submerged during sea trials, it displaces over 3,800 tons, making it the largest conventional submarine ever built by South Korea. The Batch 2 vessels are set to increase their displacement by approximately 450 tons, further enhancing their capabilities. These submarines utilize a diesel-electric propulsion system with a low-noise skew-back propeller, ensuring both quiet operation and efficient underwater maneuverability. With a maximum speed of 20 knots, 37 km per hour, 23 miles per hour when submerged, and 12 knots, 22 km per hour, 14 miles per hour when surfaced, the On Mu submarines can swiftly respond to various naval situations, from covert surveillance missions to rapid tactical maneuvers. The On Mu submarines are built to endure long missions, with an impressive endurance of up to 50 days. They can cover substantial distances with a range of 10,000 nautical miles, approximately 19,000 kilometers or 12,000 miles, ensuring they can effectively patrol and protect South Korea's maritime interests even in distant waters. Equipped with a formidable array of weaponry, the On Mu submarine can deliver a powerful punch when necessary. It features 6 533mm 21-in torpedo tubes, capable of launching Tiger Shark torpedoes and Harpoon missiles. Additionally, the inclusion of 6 VLS tubes for cruise and ballistic missiles provides the submarine with versatile offensive and defensive capabilities. With a complement of 50 highly trained crew members, these submarines are well prepared for extended missions and combat scenarios.
The process begins with the casting of blanks, which are essentially the raw material for the reactor vessel components. These blanks are then meticulously fabricated to create the shells that will form the primary structure of the reactor vessel. Flange holes are essential for attaching various components and ensuring the integrity of the reactor vessel. Precision machining is carried out to create these holes, ensuring that they meet strict dimensional and alignment requirements. Given the harsh operating environment of a nuclear-powered icebreaker, corrosion resistance is paramount. Specialized coatings and surfacing techniques are applied to the reactor vessel to protect it from corrosion caused by exposure to seawater and the extreme temperature fluctuations encountered in the Arctic. The girth weld is a critical joint that connects the two halves of the reactor vessel shell. Skilled welders use advanced welding techniques and equipment to create a strong and reliable bond. Nozzles are openings in the reactor vessel through which various pipes and components are connected. These nozzles are welded to the vessel with extreme precision. Heat treatment is often employed to relieve residual stresses and improve the mechanical properties of the welded joints, ensuring they can withstand the rigors of operation. The closing weld is the final seal that encloses the reactor vessel. This weld must be executed flawlessly to maintain the vessel's structural integrity and prevent any leakage of radioactive materials. Hydraulic chambers are essential components of the reactor's control and safety systems. They are meticulously welded to the reactor vessel, ensuring proper alignment and sealing. Inside the reactor vessel, a complex array of internals is fabricated. These internals play a crucial role in controlling the nuclear reactions, moderating neutron flux, and facilitating heat transfer. The production of a reactor plant for the newest nuclear-powered icebreaker is a complex and highly specialized process that involves several critical steps to ensure safety, efficiency, and longevity. Each step plays a crucial role in the overall performance and reliability of the reactor plant. The production of a reactor plant for the newest nuclear-powered icebreaker is a complex and highly regulated endeavor. Each step, from casting blanks to fabricating internals, is critical to the overall performance and safety of the reactor. With stringent quality control, precision engineering, and the use of advanced materials, these reactor plants are designed to withstand the harshest conditions of the Arctic and ensure the icebreaker's ability to navigate and operate effectively in extreme environments.
The journey begins with continually cast round steel billets, each boasting a diameter of 230 millimeters. These billets are the raw material used to manufacture the seamless tubular products. These billets are produced by another company within the Alpina Group in one of the world's most advanced steel plants. Most of these continuously cast billets are cut to the required lengths using carbide-tipped saws. A small percentage of billets undergo preheating before being cut to length using billet shears. An automated computer-controlled rotary hearth furnace is employed to preheat the billets to a forming temperature of approximately 1,280 degrees Celsius. This preheating process is essential for the subsequent rolling. The solid round billets then enter the cross-roll piercer, the first of 3 forming steps. Rows set at angles to each other feed the billets over an internal piercer at a speed of 1 meter per second, transforming them into tube shells. To maintain the integrity of these tube shells, mandrel bars are inserted into them. The tube shell and the mandrel bar are pushed through a stand of forming rolls, elongating the pierced shell along the length of the mandrel bar, creating a seamless tube. This process can elongate the pierced shell up to 17 times its original length, resulting in a hollow tube. These hollows can reach lengths of up to 22 meters with a minimum wall thickness of 3 millimeters. Before the hollow enters the reheating furnace, its wall thickness is carefully controlled using a radiometric gauge. Once inspected, the seamless hollows are heated in a computer-controlled walking beam furnace to the required rolling temperature for the subsequent stretch-reducing process. These hollows rotate as they pass through the furnace to ensure uniform heating. The 28-stand stretch-reducing mill is where the tubes receive their final geometry, including defined diameters and wall thicknesses. Radiometric gauges are employed again after the rolling process to verify wall thicknesses over the entire length. Inspection results are graphically displayed and documented, contributing to precise quality control. These tubes, now up to 150 meters long, can be rapidly cooled to achieve specific mechanical or performance properties. After cooling, carbide-tipped saws are used to cut the tubes into multiple or final lengths. These tubes then undergo further processing or serve as pre-material for drawing or drill pipe manufacturing plants. Alpina Tubulars provides tubes for various industries, including commercial vehicles, automotive, mechanical, boiler pressure, high-temperature resistant, and oil and gas.
The hot strip mill, HSM, described in the document, is a remarkable industrial facility dedicated to the production of steel strips with varying thicknesses and widths. This critical component in the steel manufacturing process plays a pivotal role in shaping raw steel slabs into highly versatile and sought-after products. In this discussion, we will delve deeper into the specifics of this HSM, exploring its design, capabilities, and efficiency. That slabs arrive continuously from the furnaces. Before processing, they undergo descaling and are then sized using a slab sizing press. This press allows for the adjustment of different finished strip widths based on the initial slab width. Casting machines. The HSM is designed for high productivity, and one notable feature is the ability of the casting machines to work efficiently with one casting width. This design optimizes productivity and minimizes downtime associated with size changeovers. Rolling stands. The HSM features a 2-high reversing stand and a 4-high roughing stand with an edger. This combination allows for a significant reduction in slab thickness while maintaining precision in the rolling process. The unique 6-part mill housing for the edger streamlines procurement processes and reduces lead times for critical components. Coil box. The coil box is instrumental in achieving a compact design for the HSM. This feature not only reduces overall investment costs, but also contributes to higher throughput as it ensures a homogeneous transfer bar temperature. Finishing mill. The presence of a finishing mill with the option to extend it to include a 7th stand for higher strength grades. This flexibility allows for the production of a wide range of steel products, catering to diverse industry needs. Production capabilities. The HSM boasts a substantial annual production capacity of 4 million metric tons. This immense capacity is a testament to its ability to meet the ever-increasing global demand for steel products. With the capacity to produce such vast quantities of steel strips, the mill significantly contributes to Shogun's standing as a major player in the steel industry. Efficiency is a cornerstone of successful manufacturing operations, and the HSM described in the document integrates several features to enhance operational efficiency. Compact design. The coil box, in particular, reduces the overall footprint of the mill, resulting in lower investment costs and improved throughput. Energy savings. The ability to roll slabs during hot charging not only saves energy but also increases overall throughput. This demonstrates the mill's commitment to eco-friendly and cost-effective production practices. Automatic systems. The HSM is equipped with fully automatic width control systems and a roll change system. These automation features reduce the need for manual interventions, leading to improved efficiency and consistency. Quality control. Several cutting-edge technologies, such as CVC Plus technology, roll gap lubrication, and interstand cooling, are mentioned in the document. These technologies contribute to high product quality, extended roll service lives, and efficient, environmentally friendly production processes. In today's industrial landscape, environmental responsibility is paramount. The document highlights the company's commitment to environmental protection. This includes the adoption of eco-friendly and energy-efficient production practices. Such dedication to sustainability is essential for mitigating the environmental impact associated with steel manufacturing.
1. Cutting direction and 3-point clamping. The KSS 1600 is equipped with a sophisticated cutting direction control system that ensures precise cuts. The workpiece is securely clamped at 3 points, preventing any movement or vibration during the cutting process. This 3-point clamping mechanism guarantees accuracy and minimizes material wastage. 2. Cut to weight. One of the standout features of the KSS 1600 is its ability to cut materials to a specific weight. This unique function allows operators to program the machine to cut materials to precise weight specifications, reducing material waste and optimizing production efficiency. 3. Cut-off transport. After the material is cut, the KSS 1600 seamlessly transports the cut pieces to the desired location. This automated cut-off transport system eliminates the need for manual handling and enhances workflow efficiency. 4. Weighing device. To ensure accuracy in weight-based cutting, the machine is equipped with a highly sensitive weighing device. This device continuously monitors the weight of the material being processed and makes real-time adjustments to achieve the desired cut-to-weight results. 5. Cutting speed up to 180 meters per minute. The KSS 1600 is capable of achieving cutting speeds of up to 180 meters per minute. This impressive speed not only enhances productivity, but also ensures clean, precise cuts across a variety of materials. 6. Saw type. Saw blade. It materials cutting speed, cutting feed. The KSS 1600 accommodates a range of saw types and saw blades, making it versatile for various materials and applications. Its adaptable nature allows for optimal cutting speed and feed rates, ensuring efficient material removal while maintaining cut quality. One of the crucial factors contributing to the smelter's round-the-clock production capability is its massive hydroelectric operation. Covering 90 miles of the Scottish Highlands, this hydroelectric system comprises locks connected by tunnels and managed watercourses. Constructing this system involved the efforts of over 2,000 men working tirelessly in challenging conditions. Their work began in the mid-1920s and culminated in the opening of the power station in 1929, providing the necessary electricity for the smelting process. The aluminum manufacturing process at Lochaber starts with alumina, a powder derived from bauxite, being transported to the site by rail. Inside the pot room buildings, the alumina is dissolved into an acidic chemical bath. Large amounts of electricity are then passed through anodes into the mixture through a process called electrolysis. This causes pure aluminum to separate from the mixture and sink to the bottom of the cells. The anodes themselves are eventually destroyed by the reaction and are regularly replaced with spent material prepared for recycling. All emissions, including carbon dioxide, are closely monitored and controlled. The molten aluminum is transferred to the casting room, where it is turned into various forms, such as pans or larger ingots. During casting, specific alloys may be added to give the aluminum particular properties required for various end uses. Regardless of its form, aluminum is known for its strength, lightness, and recyclability, making it a highly sought-after material that never rusts. The workforce at Lochaber is both skilled and dedicated, with an emphasis on apprenticeship programs to develop skills and provide job opportunities to young individuals. The operation, while not the largest on a global scale, holds a unique advantage. Liberty plans to construct an auto components factory alongside the smelter, allowing them to increase the value of aluminum by converting it into finished products, a process that rarely happens elsewhere. From an environmental perspective, this integrated approach is crucial as it eliminates the need for transporting molten metal to third-party facilities for further processing. After over a century of production, Lochaber looks set to continue its legacy of manufacturing aluminum, combining tradition and innovation to contribute to the global aluminum industry while promoting sustainable practices.
The journey of wheel rim manufacturing begins with a thorough analysis of raw materials, typically aluminum, alloy, or steel. These materials must meet specific metallurgical and mechanical properties to ensure the final product's strength and performance. Once the raw material passes the stringent quality checks, it is ready for the casting process. Tilt casting machines are used to create the initial rim shape. Molten metal is poured into molds designed to replicate the desired rim design. The tilting action of the machine ensures even distribution of the material within the mold, resulting in a uniform rim structure. Quality control is paramount in wheel rim manufacturing. X-ray machines are employed to examine the cast rims for any internal defects, such as air bubbles or impurities, that may compromise structural integrity. To enhance the mechanical properties of the rims, a heat treatment process is employed. This involves heating the rims to specific temperatures and then cooling them gradually. Computer numerical control (CNC) machines are the precision workhorses in the wheel rim manufacturing process. These highly sophisticated machines bring an unprecedented level of accuracy and consistency to the machining phase. Equipped with cutting-edge technology, CNC machines utilize computer programs to control cutting tools with pinpoint precision. They meticulously sculpt and refine the rough castings, ensuring that each rim meets exacting dimensional standards and design specifications. The computer-guided operations guarantee uniformity across all rims, eliminating human error and variability. To guarantee the safety and performance of the wheel rim, an air leakage check is conducted. Each rim is pressurized and monitored for air leaks, ensuring that it is airtight and free from defects that wheel rims must be perfectly balanced to prevent vibrations and ensure smooth driving. To prepare the rim's surface for finishing, a sandblasting procedure is carried out. The choice of finish is crucial for both aesthetics and corrosion resistance. Many rims are coated with paint for protection and appearance enhancement. In addition to wet painting, some rims undergo powder coating. Powder coating is a dry finishing process in which an electrostatically charged powder is applied to the rim's surface. To ensure a flawless finish, a dust-free painting booth is used during the painting or powder coating process. In pursuit of environmental sustainability, modern wheel rim manufacturing facilities incorporate air filtration systems. For high-end rims with intricate designs, a mirror face machining process is employed using diamond-cut tools. Some rims require a chrome finish for a luxurious and shiny appearance. A sputtering chrome machine applies a thin layer of chrome to the rim's surface through a vacuum deposition process. Throughout the manufacturing process, rigorous quality control measures are in place. Dimensional accuracy is of utmost importance in wheel rim manufacturing. Precise measurements and inspections are carried out to confirm that each rim meets the specified dimensions and tolerances. To assess the rim's structural integrity under real-world conditions, a bending moment fatigue test is conducted. The rim is subjected to repeated loading and unloading cycles to evaluate its resistance to fatigue and deformation. Dynamic radial tests simulate the rim's behavior when subjected to lateral forces and loads during vehicle operation. This test assesses the rim's ability to maintain stability and integrity under various driving conditions. Before the wheel rims are ready for packaging and distribution, an intensive final visual and appearance control is carried out. Every rim is meticulously inspected for any cosmetic imperfections or blemishes, ensuring that only flawless products leave the manufacturing facility. The production process at Franchini Achai begins with a careful selection of high-quality ingots sourced from reputable European steelworks. The quality of these ingots serves as the foundation for the superior forgings the company is known for. To optimize the ingot cutting process, the facility is equipped with 20 saw cutters and an oxy-fuel cutting machine. This equipment ensures precision and efficiency in preparing the raw material for forging. Forging is the heart of Franchini Achai's operations. The facility boasts a diverse range of 10 furnaces with varying capacities, up to 450 cubic meters. These furnaces are used to heat the ingots, which are sourced from both their warehousing and directly from steelworks on insulated trucks, enabling hot charging. Once the ingots reach the desired temperature, they are placed into open die presses, where they undergo a series of specialized operations. These operations include upsetting, stretching, punching, mandrel stretching, and more. Franchini Achai has 3 different presses with capacities of 2,500 tons, 3,500 tons, and 8,000 tons, each equipped with integrated and automated manipulators. This state-of-the-art equipment allows the facility to handle forged parts weighing up to 100 tons, catering to a wide range of customer requirements. After forging, the steel forgings are transferred to a dedicated heat treatment department. This critical step imparts the necessary mechanical and metallurgical characteristics to the forged parts. The department is equipped with movable furnaces capable of reaching temperatures up to 1150 degrees Celsius. These furnaces are equipped with advanced control systems to ensure precise and consistent heat treatment. The quenching process is equally important, and Franchini Achai offers options for both water and polymer quenching. The tanks used for quenching have adjustable speed propellers to ensure thorough and uniform cooling. The facility can handle heat-treated parts as long as 24 meters, and an automatic loading system allows for the treatment of multiple pieces simultaneously while closely monitoring transfer times. The entire heat treatment process is carried out under the supervision of highly qualified personnel to guarantee quality and consistency. Franchini Achai's workshop is equipped with computer numerical-controlled CNC machines for both rough and fine machining of forged parts. This includes vertical and parallel lathes, milling cutters, boring machines, and drilling machines. These advanced machining capabilities ensure that the forged parts meet the precise dimensional and surface finish requirements of customers. Quality is of paramount importance at Franchini Achai Spa, and the company's quality system is certified according to ISO 9001 to 2015 standards. Highly skilled technicians oversee the entire production process, from the selection of raw materials to the delivery of finished parts. Rigorous quality control measures are implemented, including surface quality inspections using magnetic particle and dye-penetrating examinations, internal quality control through ultrasonic tests, both manual and automatic, dimensional checks using gauges and templates, surface hardness measurements conducted with a 3,000 kilogram Bernal hardness tester, heat stability tests on rotors weighing up to 50 tons for use in steam or gas turbines. Additionally, Frankinia Chai's internal laboratory is equipped to perform destructive tests, including mechanical tests using tensile and impact testing machines, telegraphic examinations through microscopy, and chemical analysis via a spectrometer. These stringent quality control measures ensure that every forging meets the highest standards of performance and safety.
Steel production is a complex and multifaceted process that involves several interconnected steps, each playing a crucial role in transforming raw materials into the versatile and durable material that is integral to our modern world. In this comprehensive overview, we will delve into the various stages of steel production, with a focus on the operations of the One Steel Whyalla Steel Works. Our journey begins with REM Mining Consumables, a vital component of the Arium steel business. REM Mining Consumables supplies resource companies with essential mining consumables, including rail wheels and wire ropes. Furthermore, it is the largest supplier of grinding media globally, holding market-leading positions in South America, North America, and Australasia. These consumables are essential for the mining industry, providing durability and efficiency in various operations. One Steel Recycling is another essential part of the steel production process. This segment of the business focuses on the collection and processing of scrap metal. With operations spanning Australia, Asia, and America, One Steel Recycling contributes significantly to the sustainable sourcing of steel materials. Recycling scrap metal reduces the demand for virgin raw materials, conserving energy and reducing environmental impact. Before we delve into the steel production process itself, it's essential to appreciate the historical significance of the One Steel Whyalla Steel Works. Originally established as a shipyard in the early 1940s, it primarily produced vessels for use in World War II. By 1965, it had evolved to produce its first steel. Today, it stands as a formidable steel manufacturing facility, producing approximately 1.2 million tons of raw steel annually. Its rich history and growth underscore its importance in Australia's industrial landscape. The iron-making department represents the initial phase of steel production. Here, the transformation of raw materials begins. The department incorporates coke ovens, a blast furnace, and power and services. Coke, produced from about 1 million ton of coal annually, serves as the primary fuel source for the blast furnace. Inside the furnace, superheated air, coke, and iron ore from nearby mining operations, in lump and pellet forms, combine with various fluxes to create molten iron. This molten iron is the foundational material for steel production. Following its extraction from the blast furnace, the molten iron journeys to the steelmaking department. Here, the focus is on refining the composition of the molten iron to create diverse grades of steel. The basic oxygen steelmaking plant is the heart of this process. It involves reducing the carbon and silica content of the molten iron through a carefully controlled chemical process. This transformation is a critical step, as it determines the characteristics of the final steel product. Casting is the pivotal stage where molten iron is shaped into the desired forms. The One Steel Whyalla Steel Works employs two key casting facilities, the slab caster and the bloom caster. The slab caster and bloom caster use water cooling processes to gradually solidify the molten steel. This process is carefully controlled to achieve the desired dimensions and properties of the steel. The slab caster produces around 300,000 tons per year for structural sections and approximately 100,000 tons for rail sections. These products are further processed in the rolling mill complex, customizing them for various industries, including automotive, mining, and reinforcing. The final phase of the steel production process occurs in the steel products department. Here, the steel slabs and blooms from the casting facilities are shaped into their final forms. The department comprises various sections, including the rolling mill, rail finishing end, shapes finishing end, and material handling. The products manufactured in this department cater to a wide range of industries, including construction, high-rise building, rail, and more. In conclusion, the production process of steel is a multifaceted journey that begins with the sourcing of raw materials and culminates in the creation of diverse steel products that serve as the backbone of our modern infrastructure. REM mining consumables and OneSteel recycling play essential roles in ensuring a sustainable supply chain for steel production. The historical significance of the OneSteel Whyalla Steel Works underscores its importance in Australia's industrial landscape. In the heart of the foundry, the rhythmic hum of industrial furnaces has resonated since the early hours of the morning. These furnaces are the starting point for the intricate and fascinating process of manufacturing cast iron, a versatile material known for its durability and strength. The journey of cast iron from its raw form to a finished product begins with the creation of molds that will shape and define its final structure. In the molding department, skilled artisans prepare the foundation for the entire cast iron manufacturing process. They start with a model, usually made of a black, dense material, which serves as the template for the desired cast iron object. This model often consists of two distinct parts, which are essential for creating the mold that will shape the cast iron. Before the model can be used to create the mold, it undergoes a crucial treatment. A release agent is applied to the surface of the model, ensuring that it can be easily separated from the mold once it's formed. This step is essential to prevent any damage to the final product during the mold removal process. With the treated model ready, it is placed inside a large steel bracket. This bracket is specifically designed to accommodate the model and hold it securely in place. Now comes the pivotal step in mold formation, filling the bracket with a special sand resin mixture. This mixture possesses unique properties that make it ideal for mold creation. As the sand resin mixture is poured, it slowly envelops the model, gradually hardening and taking on the precise shape of the model itself. To ensure proper identification of the mold, skilled operators imprint the client's name onto the sand surrounding the model. This personalized touch ensures that each cast iron product can be traced back to its intended recipient. Remarkably, it takes only about 10 minutes for the sand resin mixture to harden. During this time, it solidifies, preserving the impression left by the model. After the sand resin mixture has fully hardened, the bracket containing the mold is carefully lifted. To avoid damaging the delicate shape created by the model, some parts of the original model are manually removed. This step requires precision and attention to detail to maintain the integrity of the mold. Once the mold is prepared, it undergoes an additional step to enhance the quality of the cast iron surface. The mold is treated with an iron oxide paint, a process known as painting the mold. This iron oxide paint serves multiple purposes. It helps to improve the final surface finish of the cast iron, aids in preventing defects, and enhances the overall appearance of the end product. Following this treatment, the painted mold is dried in an oven to ensure the paint adheres properly. With the two molds now prepared, they are positioned next to each other. The lower mold is the starting point for creating the internal structure of the cast iron object. Inside this lower mold, a core is carefully placed. The core plays a critical role in determining the internal void within the cast iron object. Its dimensions are meticulously calculated, typically being reduced by 1 centimeter compared to the mold's shape, to determine the final thickness of the cast iron at the end of the casting process. Placing the core is a highly delicate operation, as it directly impacts the structural integrity and functionality of the final product. Finally, the second half of the mold, which corresponds to the top part of the cast iron object, is rotated 180 degrees and overlaid on the first mold. The two molds now form a complete enclosed cavity that will define the shape of the cast iron product. As the manufacturing process progresses, centering pins take center stage, ensuring the precise alignment of the two halves of the molds. These small but essential components play a pivotal role in guaranteeing that the molds fit together seamlessly, preserving the integrity of the final cast iron product. With their assistance, the molds are prepared for the next critical stage. The cast iron itself undergoes a remarkable metamorphosis. In the foundry, a colossal 18-ton oxygen combustion rotary furnace stands as the crucible of this transformation. It's here that raw iron material is melted down, a process that requires patience and precision. Over the course of 2 hours, the furnace's roaring flames heat the raw iron to a blistering temperature of 1500 degrees Celsius. At this extreme heat, the iron transitions from its solid form into a molten liquid state. It's a moment of alchemy as the metal succumbs to the intense heat and becomes a river of molten iron. The molten iron is carefully poured from the furnace into a ladle, a vessel specially designed for the precise control of this crucial phase. At this point, it's crucial to eliminate any impurities that may have surfaced during the melting process. The surface of the molten metal is meticulously skimmed to remove any unwanted elements, ensuring the cast iron remains pure and of the highest quality. Precision is paramount throughout the casting process. To maintain consistency and quality, a temperature probe is employed to continually monitor the temperature of the molten cast iron. This ensures that the iron remains within the desired temperature range, crucial for achieving the correct metallurgical properties in the final product. With the molten iron prepared and quality assured, it's time for the grand finale, the filling of the molds. Each meticulously crafted and prepared mold, bearing the imprint of the original model, is filled one by one with the molten cast iron. This is where the design and engineering expertise converge with the artistry of casting, as the liquid iron takes on the precise form of the mold, capturing every detail and contour. The casting process, however, is only part of the journey. The next day, a substantial mechanical arm, resembling a sentinel, rises to action. Its purpose is to deftly separate the castings from their sandy encasement, freeing them from their molds. This step is a moment of revelation, as the cast iron pieces emerge, bearing the striking imprint of the model and revealing their unique beauty. Yet the journey is not quite complete. The cast iron components are then taken to a sandblasting chamber, a chamber of transformation in its own right. Inside, small steel spheres strike the surfaces of the cast iron pieces for a few minutes, acting like gentle sculptors, removing any remaining residues or imperfections. As the pieces exit the sandblasting chamber, they do so with a gleaming, pristine surface that speaks to the care and attention to detail throughout the entire process. While the cast iron pieces may now be impeccably clean, there remains one final task: removing any remaining burrs. This meticulous finishing touch ensures that the cast iron components are not only structurally sound, but also aesthetically flawless, ready to serve their intended purpose in a myriad of structures and industries around the world. The journey of creating a knife begins with selecting the right raw material. Common materials for knife blades include stainless steel, carbon steel, and Damascus steel, each with its unique properties. Sheets of the chosen material are cut into appropriate sizes to serve as the starting point for the knife blank. Precision in this stage ensures that the blade will have the desired dimensions and characteristics. The next step involves forging the knife blank, which is essentially shaping the blade before refining it further. The blank is heated until it reaches a malleable state, making it easier to manipulate. Skilled blacksmiths use hammers and anvils to carefully shape the blank, imparting the knife's basic design. This forging process not only defines the blade's shape, but also aligns its grain structure for durability. Once the basic shape is formed, the excess material is trimmed away, leaving behind the rough outline of the knife. Depending on the design, some knives require perforations or holes in the blade. This step is essential for specific types of knives, such as cheese knives or boning knives, as it enhances their functionality. Perforations are carefully drilled or cut into the blade, adding a unique characteristic to the knife's design. The hardening process is vital for giving the blade its toughness and edge retention. The knife blank is heated to a critical temperature, at which its internal structure transforms. This is followed by rapid cooling, which hardens the steel. The precise temperature and cooling method depend on the type of steel used, and skilled smiths must ensure consistency and accuracy in this stage. After the initial hardening process, the blade enters the crucial stage of oil quenching. This step is instrumental in fine-tuning the blade's properties. The heated blade is immersed in a carefully chosen oil bath, typically consisting of oils like vegetable oil or specialized quenching oils. The rapid cooling in oil serves to interrupt the formation of large, brittle crystals within the steel's microstructure, a phenomenon known as tempering. This prevents brittleness, ensuring that the blade remains strong, resilient, and capable of withstanding the rigors of everyday use, making it a reliable tool for years to come. The heating and cooling processes can sometimes cause slight warping or distortion in the blade. To ensure a perfectly straight knife, it is carefully straightened during this step. This meticulous process requires patience and precision to achieve a blade that is not only straight, but also true to its intended design. With the hardened blade now taking shape, it's time to start refining its edge. Grinding is a critical step in knife production. The blade is ground to the desired sharpness and shape. While most of the attention is focused on the blade's edge, the back of the knife also plays a crucial role in its performance and balance. It is carefully ground to achieve the desired thickness and taper, ensuring that the knife is not only sharp, but also well balanced and comfortable to use. After the grinding process, the knife blank is thoroughly dried. This is essential to remove any moisture that may have been absorbed during the hardening process. Drying prevents corrosion and ensures the blade's longevity. The bolster is the thick part of the knife where the blade meets the handle. Pre-grinding this area is essential for a smooth transition between the blade and handle, both aesthetically and functionally. It ensures that the knife has a comfortable grip and a cohesive design. Following the initial grinding, the blade undergoes fine grinding. This step refines the blade's edge to a razor-sharp finish, ensuring that it will perform its cutting tasks with precision and ease. Fine grinding requires great skill and attention to detail to achieve a perfect edge. Throughout the various grinding stages, debris and metal shavings can accumulate on the blade. Cleaning is an essential step to remove any impurities and to prepare the blade for the next stages of production. As a knife progresses through its grinding stages, minute particles of metal shavings and debris adhere to its surface, obscuring its clarity and potentially affecting its functionality. Cleaning is a pivotal phase that ensures the blade's purity and integrity. Impurities and residual materials are meticulously removed, unveiling the blade's pristine form. Beyond its aesthetic value, a clean blade is essential for the precision required during subsequent manufacturing phases. It facilitates the fitting of handles and bolsters with utmost accuracy, guaranteeing a seamless, ergonomic design. In the world of knife craftsmanship, this dedication to cleanliness paves the way for superior performance and craftsmanship. To ensure the handles are not only functional but also aesthetically pleasing, they are often finished by hand. Skilled artisans carve, shape, and polish the handles to perfection. This handcrafted touch adds a personal and unique element to each knife. Before proceeding further, the knife undergoes another round of cleaning to remove any residue from the handle finishing process. Additionally, an in-process inspection is conducted to ensure that all components meet quality standards. Any imperfections or deviations are addressed at this stage to maintain the knife's integrity. The final step in knife production is sharpening the cutting edge to a keen edge. This is often done on a specialized grinding stone, where the blade is carefully honed to perfection. The sharpness achieved in this step is what makes the knife truly functional and ready for use.